Good day. This presentation is a portfolio submission for studio, construction project execution and monitoring control. Part of the Masters in Construction Engineering and Management program at Chapel University, Spring Semester 2026. The project undertaken is Executive Hospitality Project presented by Group 5. I am Abhikumar Dar. This work has been carried out under the guidance of Dr. Jyoti Trivedi and Dr. Vasil Patel with the academic support from the teaching associate Mr. Naman Khamar. We extend our sincere gratitude to them for their direction throughout this semester. This portfolio covers three integrated modules: quality control, cost and tools of quality, and value stream mapping. All apply to a live construction project context. Project brief. The contextualize the work presented in this portfolio. We begin with an overview of the project. The Executive Hospitality Project is a premium hospitality and institutional development located within the plant township. It is envisioned as a modern corporate guest house offering high quality accommodation, dining, conference, and recreational facilities for corporate personnel and guests. The site spans 12,511 square meters and is situated adjacent to a residential building, a labor camp, a Repsword Educational Institute, making site logistic and critical planning consideration from the outset. Structurally, the project comprised three basements constructed using cast in situ precast method, topped by G plus 18 superstructure built entirely through precast construction. Technically demanding methodology that necessitated rigorous quality oversight. The total project cost is 410 crores executed under EPC cum item rate contract. The project commenced on 4 June 2025 and is scheduled for completion by 3rd June 2027 within a 24-month execution window. The scope of work encompasses core and cell work, MEPF, waterproofing, finishing and interior work, external development and landscaping. Four overarching project objectives guide all decisions: delivering premium hospitality infrastructure, ensuring fast and efficient construction delivery, enabling corporate brand enhancement, and achieving integrated project development. With this project as the backdrop, the portfolio addresses how quality and productivity were systematically managed on site. The first module of this portfolio focuses on the quality control laboratory, the physical and operational foundation of the project quality assurance system. A dedicated on-site QA/QC laboratory was established with a total area of 34 square meters, comprising 24 square meters of the laboratory space and 10 square meters of the curing tank. The isometric and 3D view presented on this slide illustrate the spatial layout and equivalent arrangement. The laboratory serves as the primary point of incoming material inspection and in-house testing. Every material entering the site, concrete, steel, aggregate, is subject to testing within this facility before being approved for use in the structure. This ensures that quality control is not retrospective exercise but is active checkpoint embedded into the construction process. The establishment of this laboratory also underpins the documentation and calibration system discussed in a subsequent slide, creating a traceable and accountable quality management ecosystem on site. A RACI chart and linear responsibility chart. A quality system is effective only when roles and responsibility are unambiguously defined. This slide presents the RACI framework: responsible, accountable, consulted, and informed, applied to the project quality management structure. The project manager holds accountability for five key activities, including laboratory setup, equipment procurement, QA/QC format finalization, and staff training and induction. Direct responsibility is limited to vendor list finalization, monthly quality reviewing, reporting. Consistent with a senior oversight function, the senior quality engineer carries the primary execution burden with responsibility for 12 activities and accountability of 31, spanning the complete quality chain from PQAP preparation, ITP development, IS code register, and method statement preparation, and calibration planning through the MCR segregation, precast acceptance, and DAB monitoring. This role is central to the operational integrity of the quality system. The planning engineer functions in a consultative and informative capacity, supporting drawing, verification, PQAP preparation, and documentation control without direct accountability for quality outcome. The LRC mapped this role across the four project phases: pre-construction, QA planning, drawing control and execution monitoring, precast superstructure work, and post-construction and DLP. This structured allocation of responsibility ensures complete traceability and eliminates ambiguity at every stage of quality decision making. Quality management, document method statement calibration. Effective quality management on a project of this scale re- require robust documentation. This slide presents three interconnected components: site documentation register, method statement, and equipment calibration. 9 critical documents are maintained on site, each with designated custodian. This includes the project quality assurance plan, the material inspection and testing plan, approved mixed design files, cube register for 7 days and 28 days compressive strength, slump test register, rolling margin test register, manual material inward register, the NCR and car register, precast element QA dossier. This structured documentation system ensures traceability from material received through a final acceptance. Method statements have been developed for 6 critical construction activities: concreting of formwork reinforcement, temperature monitoring of raft concrete, D-wall repair, and RCC structure repair. Of particular note is that raft concrete pour methodology. Temperature sensors were installed at 7 locations across the raft, measuring at once, middle, and 250 mm from the exposed bottom surface. Probe were fixed to reinforcement without direct rebar connect. In accordance with the approved GFC drawing, this protocol is essential to managing thermal gradient and preventing cracking in a mass concrete pour. Equipment calibration covers all 13 equipment on site, aligned with both CPWD and NABL norms. The compression testing machine, weighing balance, and hot air oven follow annual calibration cycle, while the batching plant gives direct influence on a concrete mix proportion is calibrated every 3 months. Together, these three elements form the operational backbone of quality management, providing the data and control that feed directly into the cost of quality analysis presented next. Quality management must be understood not only as a technical discipline but also a financial one. The slide presents a structured cost of quality analysis, decomposes into prevention cost, appraisal cost, internal failure cost, and external failure cost. The total appraisal cost for this project is 14,65,291 rupees. This includes external quality audits conducted by ISO QR every 6 months, 4 audits over 24 months project duration at 6,000 per visit, which is cost about 24,000. The analysis also captures granular operational costs such as a curing tank, maintenance, two labors cleaning the tank monthly over 24 months, totaling 13,440 for the project duration. The prevention cost stand at 55 lakh 40,926 rupees, reflecting the investment in staff training, method statement preparation, laboratory setup, QAP development, and inspection planning. This represents a deliberate front-loaded investment in defect prevention. The fundamental principle underpinning this analysis is that a prevention expenditure through the significant substantially reduce the internal and external failure costs. The consequence of underinvestment in prevention is demonstrated concretely in the following slide through non-conformity rework cost. The slide represents non-conformities and identify on site and quantifies the cost of rectification, making the link between quality failure and the financial impact explicit. 4 non-conformity were documented during the execution. NC1, the surface defect on the raft foundation. NC2, the concrete leakage from the shutting at lift pit. NC3, the exposed reinforcement across 6 D-wall panels. NC4, vertical gaps between adjoining D-wall panels. A detailed cost analysis was carried out for NC3 as it represents the most significant rectification effort. Material cost 48 bags of micro concrete, 10 liters of SBR bonding agent and curing materials, total about 24,900 rupees. Equipment cost, which is about 4,300 rupees. Labor cost for two mason and two helper over 2 days amounted to 4,400, including a re-inspection cost of 500 rupees. The total rework cost for NC3 was 34,100 rupees. This figure flows directly into the internal failure cost component of the cost of quality framework. It illustrates with clarity how defects that escape early detection become significantly more expensive to resolve, reinforcing the economic rationale for the prevention investment documented in the previous slide. The final component of the quality module applies a statistical process to control or validate the effectiveness of the quality system in practice. X bar and R bar control chart were developed to monitor the 7-day compressive strength of M30 concrete across 25 sample batches cast during the project. For the X bar chart, the grand mean is 27.07 MPa, the upper control limit is 28.76 MPa, and the lower control limit is 26.38 MPa. For the R chart, the average range is 1.38 MPa with UCL of 30.54 MPa and the LCL of 0 MPa. The target mean strength derived as FCK plus 1.65 into S using standard deviation of 5 MPa from IS 456 2000 table number 8 is 38.25 MPa. This corresponding 7-day compliance threshold is 22.95 MPa, which is 60% of the target mean strength. Critically, all 25 samples fall within control limit on both charts, confirming that M30 concrete production process is statistically stable throughout the casting period. Both between batch consistency and within batch variation remain fully under control, with performance well above IS 456 2000 compliance threshold. This statistical validation directly substantiate the quality investment made. The laboratory calibration regime, documented procedure, and trained personnel are collectively producing a miserably controlled and compliant output. Value stream mapping. The second major module of this portfolio applies on lean construction principle through the value stream mapping. On 27th March 2025, a structured observation was conducted from 9 am to 5:30 pm, focusing on the activity of syrup binding for syrup wall, a labor incentive, a repetitive reinforcement task, a representative of day-to-day site operational. The scope covered two shear walls of dimension 300 by 1200 mm executed by a crew of 4, 3 steel fitter and one foreman. The reinforcement comprised 36 master ring of 10 mm diameter, 18 rings of 8 mm diameter, 148 stirrup of 10 mm dia and 148 triangular rings of 8 mm dia across both walls. Total time recorded for the activity was 444.9 minutes. The VSM methodology followed a structured 5-step process: selection of the activity, workflow, comparison, current state mapping, identification of value adding versus non-value adding activities, waste identification, and future state mapping. This systematic approach enables the rigorous data-driven analysis for construction productivity, moving beyond subjective observation to quantified waste identification and targeted improvement. The current state mapping revealed that out of total lead time of 17,051 seconds, only 12,515 seconds constitute value adding work. The remaining 4,536 seconds, approximately 27% of the total time, represented non-value added waste. Categorizing waste by the time code framework, extra processing accounted for 2,350 seconds, transportation for 1,740 seconds, and motion for 1,490 seconds. Non-utilized silent for 755 seconds, inventory for 640 seconds, waiting for 480 seconds, and defect for 220 seconds. The work at a height set of activities in particular were identified as the primary source of motion, transportation, and ideal talent waste. To address this insufficiency, 4 lean tools were proposed for the future state: Kaizen for continuous improvement at the point work, Gemba work to ensure supervisory presence and real-time observation, daily huddle for morning alignment on target and resource deployment, 5S for workplace organization at reinforcement staging area, and Kanban for the control material flow to workplace. The projected outcome of this intervention is a reduction of total working time from 30,540 seconds to 24,251 seconds, and improvement in take time from 61.08 seconds per kilogram to 48.50 seconds per kilogram, representing a 21% gain in productivity for the same quantum of work without any increase in manpower or resources. This exercise demonstrates the tangible value of applying lean methodology to construction operation, where significant productivity improvements are achievable through the structured observation and targeted waste elimination. Conclusion: this portfolio has been presented comprehensive, integrated study of quality management and lean productivity across the 3 modules applied to the executive hospitality project. Module 1: the quality control laboratory established the physical, procedural, and human interference infrastructure for quality assurance on the site. The RACI framework ensures the defined accountability, the documentation system ensures traceability, and the calibration regime ensures the reliable test data throughout the execution. Module 2. The cost and tools of quality demonstrated that quality is both a technical and financial discipline. The prevention cost of 55 lakh 40,923 when view alongside the rework cost of 34,100 for single non-conformity underscores the economic advantages of proactive quality investment. The SPC analysis provided statistical evidence that a quality system is functioning as intended with all M30 concrete batches remaining within control limit across the project duration. Module 3. The value stream mapping and applied reconstruction thinking to a specific site activities and identify that 20% of the observed time was non-value adding through structured lean intervention. A 21% improvement in take time was projected, illustrating that productivity enhancement does not require additional resources but rather than systematic elimination of waste embedded in existing rework. Taken collectively, these three modules reflect the core competency of construction engineer and manager to deliver and project not merely on schedule and within the budget, but with rigorous quality, financial discipline, and operational efficiency. Thank you.